Good morning. Okay, so your next assignment is homework 4A, and if you took my advice last time, then that means you've already solved a couple of those problems. Remember, we talked about streamlines, path lines, and streak lines in the last class, and it's kind of a confusing thing learning how to draw those at first. So there's a little bit of practice in the homework assignment. A week from today, we'll have quiz number 2. Today we're talking about fluid acceleration. I wanted to make an announcement. Let's see. There is a discrepancy between the syllabus and the course policies. Someone pointed this out in class, I think it was the other section, that if you look at the course policies, it says quizzes are 12%, but if you look at the syllabus, it says quizzes are 15%. That was an oversight that I made. I was trying to make it more favorable for students by increasing the weighting on assignments and also the lab reports. But what I'll do, because of the discrepancy, at the end of the semester, I'll calculate your grade both ways, and whatever gives you the higher average is what I'll use to consider your letter grade. So you don't need to do anything. It will continue your weighted average that's shown on iLearn. It's set up according to this formula. But at the end, I'll manually, well, not manually, I'll put it into a spreadsheet, but I'll double check to see if using this weighting is better for you. Any questions about that? Just an oversight on my part. I apologize if there was any confusion. All right, so today we're talking about fluid acceleration. And so acceleration comes from two different possibilities. And what this drawing is showing is a particle that's flowing along a curved path, and this is experiencing acceleration that is both tangential and normal to its path. And so let's watch a couple of videos very briefly to give us an idea of the two types of acceleration. Now, the reason why we're talking about acceleration is not just for general knowledge. It's because we want to solve problems and answer questions once we know how fluid is accelerating. And the types of things we're going to try and find out is, how is the pressure changing? Remember, in the hydrostatic equation, we're just looking at pressure changes as we go down through a fluid. But that was when fluid isn't moving. And most of the time, fluid is moving. So we need to have equations that will tell us how does the pressure change when the fluid is moving. So to understand motion, we need to understand acceleration. All right. Here we go. So here's our first video. It's showing acceleration, and this is the sort of thing that I hope I never have to get in one of these. Have you ever seen maybe in a movie where they're doing a pilot training or astronaut training where they start to spin that and someone's inside? And it doesn't seem like it's moving very fast, but I bet it probably feels like it's moving pretty fast for the person who's inside. And the acceleration that they experience depends on two things. It depends on how quickly it's rotating, but then it also depends on the distance. So the angular velocity, or how many radians per second that is rotating through. And you can get an idea of how much acceleration they're experiencing by the angle of the little pod inside. The pod swivels as it spins. And the reason for that is you don't want to throw the person against the side of the pod, but since it rotates, then it just pushes them down into their seat and against their chair. So this is the sort of thing where if it moves fast enough, then you can start to pass out because it restricts blood flow to the brain. And when pilots are flying, they've been trained to sort of flex their stomach muscles and kind of grunt a little bit, and what that does is it traps the blood in their upper torso so that it doesn't drain from their brain and then they black out. So with those techniques, they can go beyond 10 Gs, which is 10 times the normal acceleration of gravity that we experience. So here's one kind of acceleration. We'll go into more details in just a bit. Here's another kind of acceleration, and this is another one of those things that I never want to be on. A rocket sled, as it passes by, you can see that they were testing an ejection seat at the same time. So that would be quite a ride, wouldn't it, if all of a sudden you're on a rocket sled that's accelerating and then your seat pops into the air. So why did we look at those videos? It's to discuss tangential acceleration and and centripetal acceleration. So tangential acceleration is dependent on time. And so the rocket sled, if you think about what was happening with the rocket sled, at one moment it was stopped, and at the next moment it was going hundreds of kilometers per hour. And so over time, the velocity was changing. And that's what caused the acceleration. The person was going, if that was a real person, let's hope it wasn't. The person, or the dummy that was sitting in that ejection seat, was pushed to the back of the seat when suddenly the velocity changed from 0 to forward motion. In the case of the circular motion, even when it achieves a constant speed, it's rotating at the same rate, they're still feeling an acceleration. And so in that case, nothing's changing with respect to time. So conditions are steady in the first video that we saw. But what's changing there is the direction of the velocity vector. Because remember, a velocity has two components. It's got magnitude and it's got direction. And so in the circular motion, the direction of velocity is changing, and so an acceleration is required to do that. So we can keep track of a particle's position in terms of its x, y, and z position and how those things change over time. Luckily for us, we'll usually consider acceleration at most in 2 dimensions, usually just in 1. But the first definition I'd like to roll out to you today is the idea of local acceleration. And so this is usually what people think of if I would have asked you about acceleration. If you go back into your memory about physics, you'd probably think a change in velocity with respect to time. So just acceleration, the colloquial definition, to be more specific, we're going to call it local acceleration. So unsteady flow and local acceleration go hand in hand. And so the direction or the magnitude is changing with respect to time. And you'll notice that I've bolded the time here, because that is the thing that's changing. We want to look at how the velocity is changing with respect to time. So it could be a vehicle that's accelerating very quickly because it's got rocket boosters, or I guess you don't need rocket boosters to move quick, but change over time. The other kind of acceleration, and we're going to be spending most of our class period today talking about this, is convective acceleration. And at first glance, it's not immediately clear how that's even acceleration, at least not from the conventional viewpoint that we usually have coming from physics, where we think about acceleration in terms of time. So here for convective acceleration, it goes hand in hand with non-uniform flow. So we look back up, local acceleration is unsteady, so unsteady and time go hand in hand, but non-uniform and position are the 2 things that are linked together. And we talked about that last time. We started a comparison list of steady versus unsteady and uniform versus non-uniform. But consider this nozzle. So you can think of this as similar in theory to the kind of nozzle that maybe would be on the end of a hose for spraying water. Firefighters have these kinds of hoses because a high velocity as it exits the nozzle allows the water spray to travel a further distance. And so if they want to spray water high up into a building, they need a very high velocity of water. So what happens in a nozzle like this is that water enters the nozzle at a large diameter cross-section, and it exits through a small diameter cross-section, and water is relatively incompressible. That's one of the differences between liquids and gases, is that gases are easily compressible. And when we talked about the compressibility of liquids, we found out that it requires enormous, really, really high pressures even to compress a liquid by less than 1%. And so for all purposes, we could say that liquids are basically incompressible. So the reason I bring it up is, as water goes through a nozzle like this, it's not going to become more compact. Just because we have the diameter decreasing doesn't mean the water is going to squeeze into the smaller space and exit at the same velocity. But the only way to get, if we put 1 liter in, the only way to get the same 1 liter out, if we put in 1, we have to take out 1 because there's no capacity for storage inside of this nozzle. We can't keep putting more and more water in. If it's full, the only way to get more in is to have the same amount exit. And so because of that, what it means is when the diameter gets smaller, we have to have it exit at a faster speed. We'll go into a lot of details about that in Chapter 5. That's known as the continuity principle. But the main idea is, I think you can all accept that if water enters at a low speed, it's going to exit at a higher speed because of the diameter tapering down. And so what that means is what we're seeing is an acceleration. It's a change in velocity, but it has nothing to do with time dependency. We can have steady flow. Remember, steady flow is when the conditions don't change over time. So steady means constant. It means we could have a pump putting water through this nozzle, and the pump flow rate right now and the pump flow rate in 5 minutes and 5 hours, it could stay the same flow rate constant the whole time, and yet still here there's an acceleration. And the acceleration is the water speeding up, but it's not speeding up over time, it's speeding up because of the shape of this nozzle. And so it's speeding up with position, and you'll notice that here they're defining this length L. And we're calling this acceleration in the direction of flow, and that convective acceleration occurs when flow is non-uniform. It can happen when it's steady, so we could make a matrix of conditions like this. We could have a box with 4 positions, and there could be steady, unsteady, uniform, and non-uniform. There can be all of these different types of flow. So here, what we're seeing is this is non-uniform flow. If we had steady, non-uniform. So steady non-uniform would mean that the pump is putting water into this at the same amount over time. If we change the flow rate in the pump, if we're gradually increasing the flow rate and the water is going through there, then it could be both non-uniform and unsteady at the same time. Or if we just had a straight section of pipe instead of this nozzle, then what that is that's uniform flow. Because in a straight section of pipe where the diameter is staying the same, there's no change in velocity with respect to position. And so if we had water going through here instead of that, then it would be steady if the flow rate is always the same going through this section, or it would be unsteady if we're constantly increasing and decreasing the flow rate through the pump. And so this matrix gives you the idea that it's independent. You don't always have to have steady and steady and uniform together. They can be a mix of things. And in the homework, you've got a problem where there's both a time dependency and a position dependency. And so there would be both unsteady flow and non-uniform flow simultaneously. And that doesn't make it any more difficult. It's just you have to, in your mind, sort of realize what's happening with the flow. You need to remember the definitions. Any questions about these ideas? Yes? Yeah. So you're asking about the acceleration? So the acceleration depends on position. And what we're going to look at in just a moment is how we define the acceleration is usually with an equation that depends on the shape of the nozzle. And so if it's both unsteady and non-uniform, then you'd need to know the position in the flow field and what time it is. Because unsteady means that the velocity is changing over time. And non-uniform means that the velocity depends on a certain position in the flow field. And so for a problem where it's both unsteady and non-uniform, the problem statement will define your location and what time it is. Okay, so this is that same table that we had last time, except for now I've added another bullet point. In the class on Sunday, there was only the first bullet point, because we just barely started talking about the difference between these different flow types. So last time I said uniform versus non-uniform depends on position or location. And then steady versus unsteady depends on time. So I've italicized those two so that it's easy to see the comparison. So today, what we're introducing is the different types of acceleration that cause this change in velocity. So non-uniform flow is caused by convective acceleration, and unsteady flow is caused by local acceleration. And you can see there's more space. So in our lecture next week, we'll continue to draw comparisons between these different flow types, and then remember, the whole idea at the end of all this theory is we want to solve some problems. We need equations from all of this. And at the end, once our minds are ready, we'll have some really useful, powerful equations that's going to tell us how pressure changes in fluid as it's moving from place to place. All right, so convective acceleration. We're going to do an example here, and this is one of the few times in fluid mechanics that actually you need to dust off your memory of calculus. Civil engineers don't use calculus as much as some other engineering disciplines, like the electrical guys. They use it a lot. But we use it occasionally for us. So let's look at what this is saying here. Now this is very similar to one of your homework problems, so I hope that this example will be useful. We'll spend some time going through it. We've got a nozzle, the same one we saw before, and the length of the nozzle is 0.5 meters. So that's L, 0.5 meters. We want to find out here at the middle of the nozzle, what is the acceleration, the convective acceleration. And so for convective acceleration, we're not talking about changes with respect to time. We're talking about how the velocity changes with respect to position. And so right here at the end of the nozzle, it seems like the diameter is basically parallel again. And so there's no more acceleration happening here because the shape of the nozzle has stopped changing. So there's no acceleration there. And there's no acceleration here because it hasn't yet started changing. But in the middle, those two walls are coming closer together, it seems like at a pretty rapid rate. This equation is telling us the shape of the nozzle, essentially, because what it defines is it says, depending on where you are in that transition, it tells you what is your velocity compared to the initial velocity, u naught. So u naught is our entry velocity of 10 meters per second. And so when x equals L, what will be our velocity? I mean, we can see from the picture here that it's 20, but does the equation give us that? So what I'm saying is for x equals L and our initial velocity is 10 meters per second, just as our first little exercise here, then what is the velocity? It's 20 because if x is L, then that's going to be 0.5, right? So 1 minus 0.5, that means 0.5. So 10 divided by 0.5 gives us 20. All right, so at first glance, this equation appears to be legitimate. So what we're going to do is we're going to evaluate the situation by saying at the middle, where x equals 0.25, we don't just want to know the velocity, but what we want to know is the velocity and du dx. So this whole thing together is defined as the convective acceleration. The convective acceleration is defined as the velocity at a certain location multiplied by the derivative of velocity with respect to position. Okay, so to solve this one, you may already have it in your mind. I didn't. I had to look it up. The chain rule. Do you remember the chain rule? Some of you do. Good. Excellent. Let me write it on the board here just in case it wasn't fresh in your mind. What we're going to say is du dx is equal to du dm dot dm dx. And in our case, the reason why we need to do this is that down here in the denominator, we're going to assign the variable m. We're going to call m that expression 1 minus 0.5x divided by L. All right, so let's step through the solution process here. We know that the position that we're interested in is the middle. Here is the expression for velocity. So to find out what is the acceleration here, first of all, find the velocity there, which should be pretty easy. We just put in our known initial velocity. We know x, we know L. So finding the velocity there should be easy. But du dx, we need to evaluate that at the location where x equals 0.25. All right? So I'm going to give you some time. I'm going to quit talking, bring up the lights, let you talk with your colleagues, and let's find out if we can define the convective acceleration at that point. Let me zoom in a little bit to make it easier for you to see, starting, I guess, with the chain rule. There we go. So what we're saying is we're assigning a new variable to this expression. So we're going to just call it m. So we're going to rebuild our original equation. We want to know du dx, so we're going to have, here is our du, dm, and here's dm dx. So this goes from a -1 exponent that goes down into the numerator. Then we have -2 exponent. And then we've taken the derivative of this with respect to x, so that term drops out. So does that x. All we're left with is the constant and L. Okay, so eventually where we end up is saying for the location we're interested in of 0.25 meters, that's in the middle of the nozzle, and its initial length of L, here's the overall definition of convective acceleration. It's the velocity at a certain location multiplied by du dx. So combining those two together, for the initial velocity of 10 meters per second, then it's 237 meters per second squared. And it's an interesting thing that we have, of course, the same units for acceleration regardless of whether it's local or convective. It's still, even though the change in velocity with respect to position and not with respect to time, there's still a time component in the description of how the velocity is changing. And for some students that can be a little confusing, is, you know, like if we're talking all about change in position, why is there seconds in the units that describe acceleration? But that's just because we're talking about velocity changes, and the rate of a velocity change is always going to have units of meters per second squared, even if it's convective acceleration. So I don't suppose that you're going to start loving calculus all of a sudden in fluid mechanics. I certainly didn't, but you may need to use it on one of the homework problems. And so what I'll remind you is just be sure in a case like this that you are picking the correct location to take the convective acceleration, because convective acceleration is all about a certain position in the flow field. And so in problems like this, they'll give you a formula that tells you how the velocity is changing over space, and then you'll need to take the derivative of that with respect to x so that you can multiply it by the velocity at the same location. And remember that the velocity is position dependent. So let's just refresh our idea of a few definitions. First of all, steady flow is when velocity is constant with respect to time. Uniform flow is when velocity is constant with respect to position. Now, local acceleration, which we talked about today, that's the standard idea of acceleration most people have, and that's just how velocity is changing over time. So that's the rocket sled moving forward, or the really fast car that can do a 0 to 60 in a certain amount of time. Local acceleration occurs when the flow is unsteady. Convective acceleration, the velocity at a certain location, multiplied by the change in velocity with respect to position. Now here, instead of x for the location, we're just using the variable s to represent location. But convective acceleration happens when the flow is non-uniform. Local acceleration is where we're going to get Euler's equation from, and convective acceleration is where we're going to get Bernoulli's equation from. And both of these equations allow us to understand the relationship between elevation, pressure, and velocity. Because we already have an equation that tells us the relationship between elevation and pressure. And so if I was going to draw a picture of a tank, for example, here's a sealed tank, and here's location 1, and here's location 2, and let's say the tank isn't moving. It's just stationary, it's static. And so if we wanted to know the change in pressure between the two, and then, here is up, all we'd have to do is measure the delta H between them, right? So that's no big issue. The change in pressure would be delta H times gamma. So that's hydrostatic equation. But what if this was experiencing a local acceleration? So what if this tank, instead of being held steady, what if it was being accelerated to the right? What if we set it onto that rocket sled that we saw the video of today? Would the pressure at 1 versus the pressure at 2 only depend on the elevation? No, it would depend on how quickly that tank is being accelerated. So that's an example of how acceleration is going to change the pressure-elevation relationship in a way that the hydrostatic equation can't address. So we're going to spend a couple of class lectures going over these. And
Professor, do like both the convective and local acceleration, do they cause the unsteady and non-uniform flow?
Can you say the question again?
Do they cause the non-uniform flow, or the non-uniform flow causes that?
It's like the chicken and the egg. Does the chicken come from the egg, or does the egg come from the chicken, right? Yeah, it's simultaneous is, I think, the answer. So his question is local acceleration caused by unsteady flow, or is unsteady flow caused by local acceleration? And I guess really the answer is that they're one and the same, that local acceleration is unsteady flow. So yeah, if we talk about like the physical object, the nozzle that we've been discussing so far, just to make your question more concrete, if we have a nozzle like this that's focusing the flow such that it enters slow and it exits fast, what caused that velocity to change? It's the nozzle, but we just name it. We call that a convective acceleration. So I guess us saying that it's convective acceleration isn't what changes the velocity, but it's like the physical conditions that are both in this case non-uniform, and it's also a convective acceleration. That's a good question, because I sometimes get tripped up in thinking the same sort of thing. Okay, so our next class lecture when we meet on Sunday is going to be all about Euler. So I want to give you sort of the appetizer of Euler's, just the first taste. You don't have any homework problems on this next assignment that are directly asking you to apply the Euler's equation, but it's kind of a big topic that I couldn't address in one lecture alone. So I want to introduce some of the ideas in today's class while we still have some time. Euler's equation is what we're going to use when the acceleration is local. So it's not this nozzle case, because this nozzle case, remember, is a convective acceleration problem. And when you see on an exam or a quiz a certain kind of a physical system, you should instantly think, what kind of equation applies here? Like if you see a nozzle, you should think, that's convective acceleration. But if you see a tank of water like this, the one that I was just drawing a moment ago, where it's accelerating in the x direction, and it's also experiencing g, the normal gravitational acceleration, this is the kind of situation that Euler's equation is used for. Because it's speeding up. Its position right now is slow, or 0, and as it moves to the right, it's getting faster and faster. And so there's going to be some pressure differences in this direction, as well as the pressure differences that exist vertically because of gravity. Okay, so Euler's equation, we already have the hydrostatic equation. That's something we learned about in Chapter 3. And so the hydrostatic equation we used for tanks like this. And this one happens to be open to the atmosphere. By the way, here's that little triangle at the top, and that's one of the indicators that indicates that the flow is in contact with the atmosphere. The other that we'd pointed out before is the little ripples at the surface, those dashed lines. So just so that you're learning the visual nomenclature there. It has some unit weight gamma. Maybe it's water, maybe it's not. It doesn't matter. We can just say that we have some gamma that's given, and at a certain depth, there's a certain pressure. Okay, so that's easy enough. But if it's other than gravitational acceleration, because this hydrostatic equation, where it comes from, is it comes from our definition of what is g. Because if you look at the gamma that is used in the hydrostatic equation, delta P equals delta H times gamma. Remember, what is gamma? It's delta H times the density times g. Because remember, the unit weight of a liquid is the density times gravitational acceleration. And so the hydrostatic equation does have an acceleration built in, but it's just assuming that only Earth's gravity applies, that that's the only acceleration. But what if there's some other acceleration beyond gravitational? So for instance, let's say this tank that's on the screen right here, what if this tank was accelerating up? So it was on an elevator or a rocket. It's on something that's accelerating it upwards at 9.81 meters per second squared. What do you think would be the pressure at this location, at this depth here, at a depth of 1 meter? What would be the pressure there if it has normal gravity and it's accelerating up? Would it be more than usual or would it be less than usual? It's accelerating up. More? You're right. What's your rationale there? Why would the pressure be higher if it's accelerating up? It's the sum of the two accelerations. It's just sort of like, consider what would you feel on your feet if you're accelerating upwards. You feel normally maybe 70 kilos, but if you're accelerating upwards at double gravity, suddenly your feet feel like they're holding 140 kilos, right? So here, pressure sort of accumulates in the same way, that there's the normal g, and then there are other accelerations that we handle in a similar way. And Euler's equation is going to address that.
Even if the acceleration is sideways?
Good question. Yeah, what if it's sideways instead of up and down? Euler's equation can handle both of them. Euler's equation, if this tank was accelerating to the side, Euler's equation, I'm not going to show you today. You have to wait. I can't give you everything at once. It's like, they don't want to reveal all the secrets in one movie. So in the sequel of today's lecture, what you're going to see is that there's some distance between them here, and we have our normal vertical distance, and instead of calling it delta H, I'll just call it like a delta Y. So if we know the pressure here at 1, we can find out the pressure at 2 by considering the acceleration in the x direction and just normal gravity vertically. And Euler's equation can handle that. It can handle both our normal gravitational acceleration and a side-to-side acceleration. So in this case, what if the tank accelerated up at 9.81 and delta H equals 1 meter? Well, the way you could think of it is that you would have the pressure being, first of all, the delta P due to the hydrostatic, which would be delta H times gamma. So it would be 1 meter times 9810 newtons per meter cubed. So 9810 pascals. But then there would also be the extra acceleration. So then that would be plus another 9810 pascals. So what is that? 19.620 pascals, I think. If it was accelerating up. If it was accelerating down, then there would be no change in pressure through the fluid. So think about that. That would be very interesting. If you were snorkeling, but the water you're snorkeling in is accelerating down, then you wouldn't feel any pressure in your ears. So that would be a good way to go snorkeling, but I don't think you could get like a coral reef in a zero-G environment. All right. In this diagram, it's basically the main idea that I want to introduce to you. There's so much going on here, but what I want to introduce to you mainly is the direction of the acceleration. And so here, this is just some element of water. It's a unit of water that's accelerating in this direction. So down here, this key is showing there's the x direction, the y direction, and the z direction. So L happens to be the direction that this fluid is accelerating in. And so if we measure some distance between one part of the liquid and another part of the liquid, then the pressure is going to change. So here on this face, you can see they're saying the pressure is P plus delta P. And then here on this face, it's just the pressure multiplied by the area would tell us the force that's acting on the fluid. Gravity is still acting down, but the acceleration can be in any direction. It could be opposing gravity, it could be in the same direction as gravity, or completely different from it. What we'll do when we get together next time is we're going to consider acceleration for a tank like this, both vertical, so up and down acceleration to see how that changes the pressure, and side to side to see how that changes the pressure. And remember, this is all local acceleration. And so that goes along with Euler's. And then in the following lecture, we're going to address Bernoulli's equation, which is for local acceleration. So let me just go back to these announcements and remind you that I'd encourage you to get an early start. The first couple of problems are all about flow visualization. The last few problems are just about convective acceleration. So I think it should be a relatively simple assignment for you. Feel free to stop by if you've got any questions, and I'll see you next Sunday.